This is part 2 of chapter 14 lecture. We left off talking about the acid and base dissociation constants, how to write basically equilibrium constants for acids and base reactions. And we also wrote, so here's the example of these problems that we did. We wrote reactions and then we wrote Ka and Kb values right here. And if you noticed, we had water appearing as a reactant on both acid and base reactions. This brings us to a particular point that the water is one of those substances, and there's a few of them, that we call it amphoteric, that it can act both as an acid and a base, depending on the situation is in. If it's paired with an acid, it's going to act as a base. If it's paired with a base, it's going to act as an acid and accept or donate a proton. So water can act both as an acid and a base when it's paired with an acid or base. It can do that even when it's just pure water. We call that the auto-ionization of water. So water self-ionizes, that's the auto part, self-ionizes, and basically it reacts with itself. So what happens when it does that? What is the reaction? Here's what happens. I have water in the liquid phase plus water in the liquid phase. So I have two molecules of water, and one of them is going to act as an acid and one is going to act as a base. If I stick with my colors, because we've been labeling acids in red and bases in blue. So if this first molecule acts as an acid, it's going to donate the proton to the next molecule, which acts as a base. Then what's left over from this acid is going to be its conjugate base, and what is formed from this base accepting the proton is going to be its conjugate acid. As you can see, I formed both OH minus and H3O plus ions in solution in water when it auto-ionizes. So I have OH minus and H3O plus. As you can see, the water here is acting both as an acid and as the base. One molecule is donating, which is an acid, and the other molecule is accepting the proton, which is acting as the base. As you notice, if I have this reaction occurring in pure water with nothing else added to it, I form the same amount of OH minus ions as I do H3O plus ions. This is, so their molar concentrations are going to be the same. How do we write an equilibrium expression for this reaction? Well, here it is. My K, or Kw is how we're going to call it from now on, is the molar concentration of H3O plus multiplied by the molar concentration of OH minus. And as you notice, I don't have it divided by H2O because both of these are liquid and they don't appear in the equilibrium expression. Therefore, the equilibrium expression for the auto-ionization of water, where I just have water as a reactant, is K equals H3O plus concentration times OH minus concentration. Now we've measured this value, and at 25 degrees, and we call this Kw for water, right? I just mentioned that. Kw is OH minus times H3O plus. At 25 degrees, normal room temperature, Kw has a value of 1 times 10 to the minus 14th. We have said earlier in chapter 13 lecture that the equilibrium constant values differ with temperature. They change with temperature. Therefore, Kw also changes with temperature. So as you can see, at 25 degrees is 1 times 10 to the minus 14, but at 30 degrees Celsius, it's a little higher. And we are going to assume in the problems we're going to do that Kw is only 1 times 10 to the minus 14th unless you are specifically given the value at a different temperature. There is a problem later on in the slides where we're given a different value for kW because it's at body temperature. But if it's not given to you, in those instances when it's at a different temperature, you will have the value given. If the kW is not given to you, then you will always assume that is 1 times 10 to the minus 14th. Make sure that you memorize this value and you know it very well because you will be doing calculations with that. Now going up here to this equation, this tells me that the product of the concentrations of OH minus and H3O plus in any solution will always be equal to the value for kW. They are constant, so their product is a constant, which means that if I increase the concentration of one, I will decrease the concentration of the other. If I increase the OH minus concentration, that will decrease the H3O plus concentration because the product has to be constant, 1 times 10 to the minus 14th. If I do the opposite, if I increase H3O plus, OH minus will decrease to keep their product the same number, to keep it constant. Now, how do we use this? I mean, we have these concentrations of these ions, which are very important when we're dealing with acids and bases. In fact, these are the two ions that we're going to be looking at the most when we try to understand what makes the solution acidic and basic. But how do we figure out if one solution has more or less? How do we know? What do we use? We have devised a particular scale that is called the pH scale. You may be familiar with it. You may have heard the term pH before. We use the pH scale to figure out whether a solution is acidic, basic, or neutral, or whether comparing two acidic solutions, one that has a higher pH or lower pH, one that is more acidic or less acidic, one that is more basic or less basic. We use the pH scale. What does the pH stand for? Well, the P part stands for minus log. So every time you see a P, that stands for minus log. Therefore, the pH stands for minus log, that's the P part, and then H is a species, so minus log of the concentration of H plus. Or, as we are familiar with this ion, is the same as minus log of H3O plus concentration. These are molar concentrations, which means that they have to be expressed in moles per liter. Moles of H3O plus per liters of solution. The H plus and H3O plus are the same thing. This just has the added water to it, then this doesn't. Sometimes we write it this way just for ease of writing because it's easier to write just this than to write the whole thing. But the important thing to get out of this is that the P stands for minus log of a particular concentration. And then what follows the P is the concentration of the species. So pH tells me that it's a minus log of the H concentration, H plus or H3O plus. But I can have other scales. I can have a pOH scale. The P, once again, stands for minus log. That doesn't change. What changed is the H became the OH. So now I look at the minus log of the concentration of the OH minus, not the H. So I have to have the concentration of OH minus to get the pOH value. Here I have to have the concentration of H or H3O plus to get the pH value. We can talk about a PCl, which means the P once again stands for log minus log. The Cl is the chlorine concentration. In our body, we have chloride anion concentration. And we can talk about the PCl scale, which tells us just minus log of the concentration of that species, the Cl species. If I have, for example, a pKw, this is the constant, the equilibrium constant for water dissociation or ionization. Well, that's the same as saying minus log. The P stands for minus log. And the kW is the value of kW, which is 1 times 10 to the minus 14th, etc., etc. We use the pH scale, once again, the pH scale, which is minus log of the H plus or H3O plus concentration, to tell us how acidic or basic something is. And oops, we also know, if I did not take the time here to derive where this comes from, but it comes from the fact, it comes from this. If you take the minus log of both sides, so minus log of Kw and minus log of OH minus and log of H3O plus, you will get this over here. pKw is equal to pH plus pOH. If you do the minus log of the Kw, which is 1 times 10 to the minus 14, that gives you 14, which means that the pH plus pOH always equal 14. Once again, I don't expect you to know how to derive these, but you do need to know that the pH plus pOH values give you 14. Just like you need to know that the concentration of H plus times the concentration of H minus equal Kw, which is 1 times 10 to the minus 14. This is another equation that you need to remember. And our scale, we typically, so the pH scale, we use this as an indication of the concentration of the hydrogen ion, H plus or H3O plus ion in a solution. That's what the pH tells us. The pH is equal to, once again, borrowing from the previous slide, it's equal to the minus log base 10, but minus log of the H3O plus concentration. These two are the two most important equations that you will need for this chapter. You need to memorize these both. Now you can have pH or pOH. You can have H3O plus here and pOH or pH, or you can have OH minus and pOH here. So it doesn't matter, but this is the basic form of these equations. The pH is equal to the minus log of the H3O plus concentration. This is the equation you're going to use if you have the concentration of H3O plus and you want to find what the pH is. If you have H3O plus concentration, you can plug that in to find the pH. Make sure that you know how to do this in your calculators. Some calculators, you have to hit the log button first and then enter the concentration as a number. And in some calculators, you have to enter the number first and then hit the log button. Make sure that you know and understand how to use your calculator, because you will be doing problems with these in the test, in the final. So you will need to know how to use your calculators to calculate the pH value. Note, the H3O plus concentration is going to be a small number. It's going to be less than 1. pH values, they go from 0 to 14, so they're larger numbers typically. These are much smaller numbers. Now, if you have the pH value and you're wanting to calculate the H3O plus concentration, you use this equation. So to find out what the concentration of H3O plus is, you do 10 to the minus pH value. So if I told you that the pH is equal to 2, what is the concentration of H3O plus? You would do 10 raised to the minus 2 power, because the pH is 2, and it will give you the H3O plus concentration. I have done a few problems with these, and they are embedded in the lecture PowerPoint slides, so you can follow along with the videos at those slides. Now, the normal range that we deal with, that when we talk about the pH scale, is from 0 to 14. The actual range is a little larger than that, but we're going to deal mainly from 0 to 14. And we all have either used litmus paper or have some idea of a pH meter, how to measure the pH. And obviously, as I said, we're going to focus from 0 all the way to 14 for the pH scale. But here's what it looks like. A pH of 7 is considered a neutral pH. This is where the concentration of H3O plus and the concentration of OH minus are equal to each other. They're exactly equal, and therefore they neutralize each other, which means obviously you have a neutral compound or a neutral solution. It's neither acidic nor basic because their concentrations are exactly equal. If you have an acidic solution, that means that you have more H3O plus ions than you do OH minus ions. So you have an excess of H3O plus. And remember I said when you multiply, so Kw is equal to H3O plus times OH minus. If H3O plus goes up, OH minus has to go down to keep their product equal to the same constant, 1 times 10 to the minus 14, which means that if this goes up, the OH minus goes down, you have what is called an acidic solution. And typically those values are less than 7. So for acidic solutions, you will have a range from 7 to 6.9, so just before neutral. Those are considered acidic solutions. The opposite is true with basic solutions. In these solutions, the OH minus concentration is larger than the H3O plus now, and that means you have an excess of OH minus ions. That makes the solution basic. These values are from 7, a little higher than 7, all the way to 14. This is for the pH scale. The pOH scale is the opposite. It goes in the opposite direction. The pOH scale, you have 0 to 7 is basic, and 7 to 14 is acidic, but that's the pOH scale. The pH scale, which is mostly used, you have 0 to 7 is acidic, and 7 to 14 is basic. And then 7 exactly is a neutral solution. That's because the concentration of H3O plus and the concentration of OH minus is exactly the same, and it comes out to be 1 times 10 to the minus 7th molar. 1 times 10 to the minus 7th molar gives a pH of 7. If you have higher numbers than that for H3O plus concentrations, meaning less negative numbers, obviously, because we're talking about the minus power. So less negative numbers will give you an acidic solution. More negative, so larger negative numbers will give you a basic solution. So if you have, for example, 1 times 10 to the minus 8th molar H3O plus, that means that 1 times 10 to the minus 8th is less than 1 times 10 to the minus 7th, which is the concentration of H3O plus at neutral solution. If you have less H3O plus, that means you have more OH minus, which means the solution is basic. If H3O plus is 1 times 10 to the minus 3, that is much larger than the neutral solution concentration for H3O plus, which is 1 times 10 to the minus 7th. If you have a larger concentration of H3O plus, that means you will have less of OH minus, which means that you will have an acidic solution. Let's look at some common compounds that we know and look at the pH of them. We'll start with seawater. Seawater has a pH of 8.5. Remember that pH of 7 is neutral. Anything from 7 to 14 is basic. So you can see that these two are blue to go with our color coding here. They're basic solutions. The seawater is basic because it has a lot of minerals dissolved in it, and they produce OH minus in solution. We're not going to talk about those types of equilibria, but know that the seawater is actually basic. Blood, our blood, is also basic, slightly, not much, but slightly basic, a pH of 7.4. Once again, you compare these to a pH of 7, which is the neutral pH. Now let's talk about all of these compounds that we consume, well, some of these anyway, we consume, and that are acidic. Rainwater, we don't consume rainwater, but we have to deal with it. Rainwater is 6.2 pH, which means it's less than 7, which means it's acidic. You probably have heard of acid rain. That's what happens. The rain is acidic, and when it rains, the acid can react with certain salts and dissolve them, and that's why we get damage from rainwater, from years of exposure to rain, acidic rain. Coffee, which most people drink, has a pH of 5, so it's quite acidic actually. And then we have tomatoes. Tomatoes are even more acidic than coffee, 4.2. Orange juice, here's orange juice, 3.5, and that comes from that citric acid that we talked about. So we have we have a lower pH for orange juice. And then the gastric juice, which is the juice of your stomach, look how low that pH is. pH of 1, very, very acidic. It's towards the lower end of the scale, so it's quite acidic. The lower on this scale, the more acidic you are. The higher on the scale, the more basic you are. The stronger the acid, the stronger the base, right? If you're closer to here, that's a weaker base than up here. If you're closer to the neutral, that's a weaker acid than towards the end of the scale, or the beginning, however you want to look at it. So gastric juice, having a pH of 1, is pretty strong because it's mainly HCl, which is a very strong acid. This is why it's important that we brush our teeth, because most of the things we consume are actually acidic, and acids will react with the enamel in our teeth to break it down, and therefore you want to wash that off to make sure that your teeth don't get damaged. Now I have these problems. I have them worked out where you have to calculate the OH minus concentrations for these solutions when you are given the H plus or H3O plus concentration, and you are asked to figure out if it's acidic, basic, or neutral solution. You can click here and watch those videos that show you how to do that. I embedded them this time instead of having them listed on JetNet. This is a lot easier this way. Here's another example, or two examples, of calculating pH of a solution when you're given the H3O plus concentration, and when you're calculating the pH of a solution when you're actually given the OH minus concentration. Once again, click on this and it will take you to a video that explains both of these examples. But these are just some calculations that we can do knowing the pH values, or if we're given the concentrations, to try to find the pH. Here's another example, and here's the one that I told you will have a different value for Kw. In this problem, the temperature is 37 degrees, not 25. So Kw, because it's temperature dependent, it's going to be a little higher than 1 times 10 to the minus 14th. And in this case, you are given the value for Kw. The relationship doesn't change. H plus times OH minus still gives you Kw, but in this case, Kw is a little higher than at room temperature, which is 1 times 10 to the minus 14th. Once again, click the link and watch this problem, how it's worked out. These are percent ionization calculations, where you have to calculate the percent ionization given the initial concentration of the acid and the pH. we can use the pH value to calculate the H3O plus concentration. And remember, the percent ionization is given as the H3O plus divided by the concentration, the initial concentration of your acid times 100. Once again, you can click on that and it will take you to the video that shows you how to work these problems. In this one, it's just the opposite of this. You're given the percent ionization and the pH where you can find the H plus, and you're asked to find the molarity of the initial concentration of your solution, of your acid solution. Please ask any questions. So after you watch these videos, if you still have questions, please ask them. These problems, the Ka and Kb calculations from equilibrium concentrations, are calculations that we're going to do if we are given molar concentrations for each of the species, and then we're asked to figure out a Ka value for some of these. I think for all of these are Ka, and the last two are Kb values. I have written out the equations for all of these so go ahead and watch the videos. I have shown you how to write the equations, write the Ka and Kb expressions, and then use these values that you are given to calculate the Ka and the Kb values. I've also used these problems to show you how to compare the strength of an acid or a base depending on their Ka values. So look at those and ask any questions if you have them. We talked about the strength of acids and bases. Strong acids and bases are considered strong electrolytes. Think back in chapter 11 when we talked about electrolytes. Because they totally dissociate in water, they are very strong electrolytes, because now you have charged species in solution that can carry a current. So that's what a strong electrolyte is a solution that contains ions which can carry a current. Because they are strong acids and bases, they're strong electrolytes because they split almost completely, pretty much completely, into their ions in solution. Therefore, their Ka and Kb values are very large. And we also talked about the strong acids and the strong bases. Both of these groups are very strong electrolytes. They conduct a current very, very well. Weak bases and weak acids do not. Because they don't have total dissociation in water, and their Ka and Kb values are small. Now this part is not really anything new other than we call these strong electrolytes or weak electrolytes, because we already talked about these in relative strengths and weakness, strength of acids and bases. However, when we go to do calculations with these, just like the ones that I have here, and I am missing that link, but I will put that here. It's whenever you have a strong acid solution, the most important thing to keep in mind as you go through and watch these problems, how I've done it, is that whenever you have a strong acid solution, you assume complete dissociation, which means the molar concentration of the initial molar concentration of your acid is going to be the same as your concentration of H3O plus in solution for all of these. That's because HNO3 completely dissociates into H plus and NO3 minus, which means that all of this is going to give you H plus. Whatever, if you have 1 molecule of HNO3, that's going to give you 1 molecule of H3O plus. If you have 1.3 moles of HNO3, that's going to give you 1.3 moles of H3O plus. If you have 0.167 molar, which is moles per liter, obviously it's the same volume of solution for HNO3 and H3O plus. Therefore, 0.167 molar HNO3 is going to give you 0.167 molar H3O plus. And this is the same, that's the basis for all of these problems with strong acids. Now, that's not always true for weak acids and weak bases. They do not completely dissociate into H2O. They have low Ka and Kb values. Therefore, the initial concentration of the acid or the base is not going to be equal to the concentration of H3O plus or OH minus. That's why we do percent ionization. That is not all, it's not for weak acids and bases, it's not going to be 100%. This will involve equilibrium calculations, and we are not going to really go into the harder type of equilibrium calculations. They can get pretty intricate, but just know that for strong acids and bases, the initial concentration of the acid is going to be the same as the concentration of H3O plus. The initial concentration of the base is going to be the same as the concentration of OH minus. For weak acids and bases, these are not equal. So you can't say, oh, I have 0.5 molar of acetic acid that's going to give me 0.5 molar of H3O plus. That is not the case because you don't have 100% ionization. However, when you do equilibrium calculations with weak acids and bases, you can calculate H3O plus or OH minus. And once you know those, you can calculate a pH, but we're not really going to go into too much detail. Just know that for weak acids and bases, you don't have complete dissociation, so you cannot equate the amount of acid initially to the amount of H3O plus, just like we did here, where we have this amount of strong acid is going to give me the same amount of H3O plus. If I had a weak acid here, I couldn't say that, and I would have to do equilibrium calculations to figure that out. Now, how are we know that acids and bases, or acids and conjugate bases, or bases and conjugate acids are related to each other by a proton. Therefore, we can also relate their Ka and Kb values. And now I will show you how to derive that. You don't necessarily have to know how to derive it, but know that you will know that the product of these will be equal to a constant. But here's some common values for Ka and Kb for acids and bases. You can see HF has 6.8 times 10 to the minus 4, but F minus has a Kb value of 1.5 times 10 to the minus 11. Much, much smaller, so much weaker base than it is an acid. The acid is much stronger than its conjugate base, etc., etc. So we can, you notice that as the strength of the acid decreases because the value of the Ka value is getting smaller, the strength of its conjugate base is increasing. So the conjugate base is stronger than the acid, than the original acid. We can relate the product of Ka and Kb by Kw. Remember this? We've seen it before. So Kw is equal to the product of the Ka times the Kb value for an acid and its conjugate base. Why is that? Well, if this is my acid, here's how the derivation happens. If I have an acid and I add it in water, I get my conjugate base and H3O plus, and I have a value Ka related to this equation. Now I could say the same thing for the base. If I take the base, A minus, and I put that in water, I form the conjugate acid plus OH minus, and it has a Kb value associated with it. Now what happens when I add these two together? When I add these two equations together, I will cancel out any species that appears both on the reactant and on the product side at exactly the same species. HA appears the same here and here, so this can cancel out. A minus appears the same here as it does here, so I can cancel these out. And what do I have left? I have 2 molecules of water, so 2H2O liquid, giving me one H3O plus and one OH minus right here. Well, what is this? This is the dissociation. This gives me the autoionization of water, Kw, right? We had H2O plus H2O, which is 2 molecules of water. So 2 H2Os give me, this is the autoionization of water, which is equal to Kb. Anytime I add reactions together, their values, the K values, are multiplied. So Kw is equal to Ka times Kb, and that is why we get this relationship between an acid and its conjugate base. If I have an acid and a conjugate base, the value of Ka for the acid multiplied by the value of Kb for the conjugate base gives me the water autoionization constant, which is 1 times 10 to the minus 14. This is also true. So just like Kw is equal to OH minus times H3O plus concentrations, it is also equal to Ka times Kb, which means that I can figure out a Kb value if I have a Ka value, because I know that this is 1 times 10 to the minus 14. So I can calculate the Kb value if I'm given the Ka and vice versa. That is what I've done here with these problems. You have the Kb, for example, the Kb value for this ion is this. Then calculate the Ka for the conjugate acid. We can use that relationship, Kw is equal to Ka times Kb, where Kw is 1 times 10 to the minus 14. Kb is 2.17 times 10 to the minus 11. We calculate Ka. Same thing over here. So once again, click on the link and watch these two problems. This is the end of this part, the acid-base part of the chapter 14. We're also going to touch a little bit, we're going to talk about the buffers, buffer solutions, and what makes a buffer and why are they important. But I am going to stop here for part 2, and I'm going to do another video for part 3 just to kind of break it up a little bit so it's not all in one large file. And part 3 is going to pick up on the buffers.